So today we will talk about quotient difference, or known as the different quotient. The short definition for a different quotient is just the change in y over the change in x, which cut down to a definition of a slope. Now to start, we will draw a graph with two axes, as we would normally would, an x-axis and a y-axis. And follow that, we will draw a curve. And on this curve, we will make 2 points that are connected by a line, and this line is known as the secant line. Now, the definition of a secant line is a line that touches 2 points on a graph. And the first point of the secant line, we will call it x. And the second point of the secant line, we will call it x plus h. And the reason to that is because in between x and x plus h, there is a gap. And we would like to call that gap by a variable, and we would like to call that h, representing that gap. Now, in the y direction, the first point is known as the function of x, and the second point we will be calling it the function of x plus h, or f of x plus h. Now, to find the slope, we will use the same idea of delta y over delta x, or the change in y over change in x. The change in y in this case will be the difference between f of x plus h minus f of x. And f of x plus h will represent y2, whereas f of x will represent y1. And the bottom, we will divide all that by x plus h over minus x. And x and negative x will cancel out, so we will end up with f of x plus h minus f of x over h. And this is the quotient difference.
Okay, so in this demonstration, we're showing how the secant line becomes the tangent line to the curve. Okay, so we start off with the graph of our initial secant line, and our goal here is to use the quotient difference formula to find the derivative, or the instantaneous slope. So we have to set h to equal 0. And during this short time lapse, we see what happens to the limit as h approaches 0. So we choose 2 points on the graph, and gradually they start to appear as if they're getting closer to each other, and as they get closer and closer to each other, they start to look like there's only 1 point. In reality, if we zoomed in, it's probably not going to be exactly at the same point, but since the h value is going to end up so small, we just assume that it's 1 point. And pretty much that 1 point becomes the tangent line, and we just draw a line along it, and it becomes the tangent line to the curve. And yep, that's pretty much it. And there you have your tangent line to the curve.
Alright, now we're going to try to find a derivative of an equation given a x value. So derivative is basically instantaneous slope, or instantaneous velocity, whatever we can say, at a certain point in x. So we're going to do this by first giving an equation, x plus 3. And then let's say we're going to try to find the instantaneous slope at 3. I'm sorry, I said equation here instead of slope, but that's what the sheet says, slope, so I'm gonna find the slope. So we have to plug it into the quotient difference formula to find the derivative, because the h in the derivative at instantaneous point or instantaneous slope is really close to 0. It doesn't get exactly to 0, but it's such a small number that we're going to assume the h is 0 at the end. So it's going to be like h is going to be like 0.0001. So the quotient difference formula is the limit as h approaches 0. So here we plug it into the equation, and I messed up on the right side of the minus sign because f of x is not f of x plus h, it should be x plus 3. So here I make the correction and I cross out the h, and then this is 3, so we're going to end up having h over h. Since h is not necessarily 0 but a number really close to 0, we can finalize that the slope or the derivative of the equation x plus 3 at x equals 3 is 1. And that's it.